So let me try to bring algebra as well, the best way I can to physics. So let's assume we have a point, and I'll call it S because in the notes it's called S. The point S is a point, and I assume that that point moves along the line on its own. I'm not pulling it, I'm not pushing it. It lives its own life, moving there, maybe flying. It can only fly along this line. And what I want is, I want to look at the distance from P to S. And that's what I want to minimize. Right? Now, what algebra tells me is I have to think of that as a function somehow. Well, a function of what? And then take derivative.
Function of position.
Function of position. Function of S, yes, function of position of S. So you can think of this quantity, PS. Well, P is fixed, right? S is changing. So the whole thing can be thought of as a function of S, because that's the changing thing. Now what we can do further, trying to reduce it to calculus 1, because in calculus 1 we have only one variable, and it better be a number. It should not be a point. So in order to reduce it further, we can think of as positioned depending on time. Basically, at any time, you know where that point is. And that position is, therefore, a function of time. So you can think of this well, maybe I should switch notation at this point. Distance from P to S is going to be distance from P to S that depends on time. And now this is going to be the only variable in the whole expression. And S being something in terms of time. And then what? Well, then algebra suggests, well, why don't we take that, a function of one variable, and we differentiate it. Equate the derivative to 0, and so can we differentiate that? I hope at this point you know how to differentiate the distance. Right? How to find derivative of the distance between two things, 2 points. Well, in order to do that, the standard thing is to interpret the distance as we did last time. What is it that we did? Dot product. Right? We use dot product. So we looked at the vector from P to S. So let's look at this vector. We take vector PS, we dot product with PS, and that product is equal to the square of the magnitude of PS. And as we take the square root, we get the distance. And the advantage of this long expression, which is more complicated than the distance, is that we know how to differentiate the dot product. It satisfies the product rule. So this is what we now want to differentiate. And let me just differentiate it. I know how to differentiate the square root. It's 1 over 2 square roots of the same expression, ps dot ps. And then I have to multiply by the chain rule by the derivative of that dot product, ps dot ps. And derivative of dot product is by the product rule, ps prime dot ps plus PS, the first PS, dot PS prime. Everything divided by 2 square roots of PS dot PS. And of course we can simplify the numerator. It is twice the dot product. 2 cancels. So I have PS dot PS prime in the numerator divided by the square root of PS. Well, let me just replace the square root of dot product with magnitude of the vector PS. That's what the square root is. Because I don't really care about the denominator, for the reason that what I want is to solve equation this equals 0, which makes the numerator equal to 0. And that means that, so this means that PS dot PS prime must be 0. And that means what? What does it mean that 2 vectors make dot product equal to 0?
Parallel, perpendicular.
They're either parallel or perpendicular. Should we vote on perpendicular? Isn't that right? Dot product equals 0 means they are perpendicular. So the vector PS is perpendicular to the vector PS prime. Finally, the word perpendicular shows up in this algebra. Because it never happened in the first solution. Now it finally happens. Now can we see that? So what is PS? Well, PS is basically a vector from P to S, and it changes as S moves. What kind of vector is PS prime? Derivative of PS with respect to T. Well, the way to think about it is that if you think of PS being position vector, just pretend P is the origin of coordinate system. So you have position vector. Remember that Kepler's law? The position of a planet. In this case, planet moves along a line. What is then the derivative of the position vector?
Velocity vector.
Isn't it velocity vector? Isn't it what we learned in physics? Derivative of position is velocity. So that vector is velocity vector of that particle. Now let me ask you this. If a particle moves along a line, what can you say about the velocity vector of that particle?
Follows the path of the line.
Isn't it always along that line? One way or the other, but always along the line. It cannot be any other. It cannot have any other direction. So that we don't know what that velocity vector is. We know that this vector PS prime, the velocity vector, is directed along the line. And then what does it mean that these 2 vectors are perpendicular? Well, that means that position vector is perpendicular to the line. And that brings us back to physics idea. And now we recovered the relation. So where is this concept of being perpendicular in that algebra solution? So let's go back to algebra. Isn't it exactly this condition? Derivative equals 0 exactly means that 2 things must be perpendicular geometrically. So isn't it a better way of understanding algebra? When you not only crunch the numbers and formulas and manipulate them and solve numerically the equations, but you also follow the track and you know what those operations mean. And isn't it great to bring algebra and do things like in general? conceptually. Instead of writing down what P is, well, it is 5, 2, and S, y equals 3x minus 2, and crunching numbers here. So this is what we hopefully should be able to do by the end of semester. On one side, doing analysis, computation, more conceptually than calculus one way. And on the other hand, even if you do computations numerically, you can still interpret what you are doing conceptually. So basically all I'm trying to do is to push you up to the next level of understanding of calculus from the basic numerical computational level and following certain procedures to the level of understanding those procedures and interpreting them from different points of view.